Hello, this is Professor Bennett from digitalaudiotheory.com. This programming example, 10.6.1, we will develop a proportional parametric equalizer. These are a class of first and second order filters that are low order and tunable equalizers whose dB magnitude response is proportional across all frequencies to a common dB gain control parameter called K. These filters can be cascaded together, creating parametric EQ. The shelving filters are first order and depend on two parameters, K and T, where K is the linear gain and T is representative of the shelf edge. While the band gain and cut filters are second order and also depend not only on K and T, but another variable, C, as well. C represents the center frequency of the filter. But for the second order band filters, the parameter T takes on a slightly different role. Here it is representative of the bandwidth of the band instead of just the band edge, as in the shelf filters. A three-band parametric EQ includes a low shelf with selectable cutoff and gain, a center band with selectable frequency, bandwidth, and gain, as well as a high shelf with selectable cutoff frequency and gain. These three filters will be cascaded, resulting in a fourth order EQ. The coefficients equations for the proportional parametric EQ will be implemented in code straight from the textbook Digital Audio Theory. The EQ will be analyzed using the freq command with each individual filter and multiplying the results together. In this example, we will apply a bass boost of 4 dB plus 4 dB with an edge of 100 Hertz. We'll put a narrow cut of 3 dB right at 500 Hertz with a bandwidth of just 100 Hertz and a slight tilt of plus 1 dB above 4K. For each section, we first compute omega, K, and T, and also C in the case of the band filter. Then we compute the coefficients A0, A1, B0, and B1 for the shelving filters, but also A2 and B2 for the band filter. So let's see that. We set our sample rate to 44.1. For the low shelf, we said we want that to be at 100 Hertz, so that gives us our omega low. We said that K depends on the gain, so we pass that in. Here's our proportional gain factor and our low edge to get T. From that, we can get our A0, A1, B0, and B1 coefficients. Let's skip ahead to the high shelf, which looks very similar, right? We're going to use an upper edge of 4K, a gain of 1 dB. We'll calculate our K and our T for the high shelf, and then that will give us our A0, A1, B0, and B1 for the high shelf. Now looking at the center band, this is going to be a second order filter centered at 500 Hertz. We said it's going to have a bandwidth of 100 Hertz, and it's going to have a gain of negative 3 dB. So we'll calculate all of those. From that, we can get our mid-band, A0, A1, A2, B0, B1, and B2. So lastly, we're going to use freq to give three complex frequency responses by passing the numerator and denominator coefficients along with the sampling rate. So here's our high shelf, which will give us our high shelf frequency response. Here's our low shelf coefficients, giving our low shelf frequency response. And here is our mid-band set of coefficients, giving our bandpass frequency response. So we'll calculate all of those. Then, to see the overall EQ curve, we're going to multiply these three frequency responses together. We're going to take the absolute value of the product and take the dB of that, and that's going to give us our overall EQ curve. Let's take a look. There you have it. We have our 4 dB boost on our low shelf, our 1 dB boost on our high shelf above 4K, and our little 100 Hertz, very high Q factor 3 dB cut right at 500 Hertz. there you have it. In the next programming example, we're going to take a look at Chapter 11, which is going to be on looking at capturing impulse responses. Until then, thanks for watching.